Classic Simplex Algorithm. The geometric method of linear programming for optimizing a linear function subject to a set of linear inequalities is limited, since it is only useful for problems involving two variables and cannot be used for problems involving three or more variables. Therefore, a simplex algorithm must be developed. The simplex algorithm is used routinely on many problems involving hundreds of variables and problem constraints. These are just a few examples of the problems used. A linear programming problem is said to be a standard maximization problem in standard form if its mathematical model is of this form. Here we'll use this example. Consider the linear programming problem of maximizing z under these constraints. This is a standard maximizing problem. From the graph, we can see there are several lines parting the feasible region. The coordinates of the intersecting point can be found by solving the set of two equations in two variables. From the graph, we can find that some of the points are corner points of the feasible region and some are outside. This is the pseudocode for the algorithm. Please pause the video and go through this yourself, especially after watching this full video. This is the algorithm for the simplex. Firstly, we rewrite the system in standard form. Then we convert it into slack form. Find the basic solution, pivot, and iterate. So from this, we increase one positive non-basic variable without breaking the non-negative constraint. To find the tightest constraint, rearrange the equation with the constraint in terms of the non-basic variables and substitute this into all the equations. This is the pivot step. We repeat this until all non-basic variables in the objective function are negative. We'll learn this by example. So we're going to solve this problem. The first thing we must do is to maximize the objective function. From here, we will change the variable size signs to maximize. Then we must ensure all variables have non-negative constraints. Y should be greater than or equal to 0, but we haven't got that, so let y equals x2 minus x3 and give x2 and x3 a non-negative constraint. We must ensure we have inequalities instead of equalities. To solve this, we rewrite the equality as two inequalities. We must also ensure that inequalities have the right signs. Basic variables should be less than or equal to the constraint. If not, invert the signs of each variable and change the sign. This is now in standard form. From here, we convert the program to slack form. To use the simplex method, the constraint inequalities must be converted to inequalities. To use the simplex method, the constraint inequalities must be converted to equalities. To make this into a system of equations, we are now introducing slack variables. Slack variables take up the slack between the left and right hand sides of the inequalities, and they must be non-negative. It is a very important step for being able to identify all the corner points of the feasible set. A basic solution can be found by setting all the non-basic variables to 0. Right now the optimal solution is 0. So let's begin the pivot step. Choosing any positive non-basic variable, let's choose x1. We find the tightest constraint on x1, which is 9. Therefore, we rearrange equation 4 to obtain an equation in terms of x1. Then we substitute this equation in all the other equations where x1 appears. Notice that x1, which used to be a non-basic variable, is now now a basic variable. The opposite is true for x6. This is the pivot. The basic solution can be found again. The optimal solution is now 27. Checking the objective function, we can see there is still a positive variable x3, so we can iterate. We find the tightest constraint on x3, which is equation 4, and again rearrange it for x3 and substitute this equation into all occurrences of x3. The optimal solution is now minus 73. We do not iterate again as the objective function contains all negative non-basic variables. The optimal solution has been found and the algorithm can be terminated. The simplex algorithm can be exponentially complex in the worst case. We will introduce an example, which is the Klee-Minty cube. The Klee-Minty cube is a unit cube in n dimension, whose corners have been slightly perturbed. Klee and Minty demonstrated that Danzig's simplex algorithm has a poor worst-case performance. The Klee-Minty problem shows that, in the worst case, it can take 2 to the power n minus 1 pivots to solve a problem in n variables and constraints. By the figure example, we can see that by starting from some vertex and choosing certain pivot rules in the simplex algorithm, it takes exponential time to achieve optimality. Also, there's no guarantee which vertex to start with when using the simplex algorithm. We are able to assume that we start from this very vertex, which leads to an exponential length path to the optimal solution. For any n-dimensional cube, this path starts at x equals 0 and visits every vertex exactly once. Thus, it forms 2 to the n minus 1 pivot, noticing that, however, only one pivot is necessary to reach the optimal solution, in which the simplex algorithm requires 2 to the n minus 1 iterations. The simplex algorithm can be exponentially complex in the worst case. For example, if n equals 100, 2 to the n, or 2 to the 100, is equal to 1.3 times 10 to the power 30. At 10,000 iterations per second, this problem could take 4.1 times 10 to the power 18 years to be solved by a computer. However, we are solving problems with variables larger than 100 every day. Also, the simplex algorithm must terminate. There are a finite number of different vertices that the algorithm can visit. So if it doesn't visit the same vertex twice, it must terminate. If it does, then it will repeat the sequence of vertices between the first and the second visit to the repeated vertex over and over again. To summarize, the simplex algorithm finds its optimal solution to a linear program. It iterates through vertices to find the smallest objective value, which at the end is the optimal value. Basic variables are selected arbitrarily, and the remaining variables are non-basic variables. We obtain a basic solution by assigning the non-basic variables a value of 0 and solving for the basic variables. If a basic solution has no negative values, then it is a basic feasible solution. Moreover, a basic solution or a feasible basic solution corresponds to a vertex of the feasible region. We can determine the feasibility of a basic solution simply by examining the signs of all the variables in the solution. And to run the simplex algorithm, follow these 3 simple steps.